Thank you for the introduction. Good morning, everybody. My talk today will be focused on CO2 emissions and evidences that we see in discrepancies between certified CO2 emissions, type approval CO2 emissions, and real-world CO2 emissions, and what we can expect with the new WLTP procedure regarding this gap that currently we are seeing. First, I'll spend some time explaining briefly, most of you know this, type approval system in Europe. And as you know, a number of tests are done on one vehicle that is representative of vehicle family. That means not all vehicles in the family undergo this type approval procedure. And under supervision of type approval authority, technical service that is appointed by each member state, all these tests are done following Directive EC 2007-46. My talk today will be about type 1 test. With type 1 test, results that at the end we get are related to fuel and energy consumption, CO2 emissions, and regulated pollutants, NOx, CO, particle mass, particle number. And currently in Europe, type 1 test is carried out according to UNECE Regulation 101 and 83. 101 is mostly referring to CO2 emissions and fuel consumption, and the Regulation 83 covers all aspects of type approval procedure, all type 1, type 2, type 3, all type approval tests. And both these regulations in Europe are known as NEDC procedure, New European Driving Cycle. Although it's very old, still has this name. And beside Europe, it's used also in several other countries. The basic parts of this procedure is that in NEDC procedure, all type approval procedure for type 1 test is described how the vehicle is coasted down on the road to measure rolling resistance, aerodynamic resistance, in total forces, resistances of vehicle to progress. And then in the next step, these forces are transferred to the chassis dyno, to the lab, to find chassis dyno settings to reproduce that the same vehicles, that the same resistances that vehicle experience on the road to reproduce in the lab. In the next step, lab test is done following prescribed procedures for the testing conditions, test temperature, humidity, also following the well-prescribed test cycle that of course has some flexibilities, some tolerances. And as a result, for what my talk today is focused, we get a CO2 value. Actually, one important difference between CO2 and pollutants is that for CO2, absolute value is important. And it's regulated on the basis of fleet-wide averages. For pollutants, not absolute value is important, but just as important that all pollutants are below set limits. And in Europe, at least for two purposes, this CO2 emission value is used. It's used to set the target for each OEM and to check the compliance of OEM every year against its set target. And also it's important for consumer information, for labeling purposes. And with all this, lab test is of course important, needed, and implemented worldwide. And it assured that all OEMs, all vehicles have a level playing field. Also that test is repeatable, reproducible, that we can do inter-lab comparisons. And a certain gap that exists between a lab test and real-world emissions and CO2 is, of course, considered normal. But with some new vehicle technologies that are being deployed regularly, we saw that these vehicle technologies can deliver different reductions that are seen only in the lab and not seen during the real world operation of vehicle. And that can result in a problem in this gap. Some history of the gap. It started to be apparent around 2005 with some historical value of 10–15%. And it's not only European issue, it's seen also in other markets. And several researchers attempted to quantify this gap based on different available sources. Emission inventories, vehicle simulations, fuel cells based estimations. And now there is increasing evidence that in Europe this gap becomes very significant, around 40%. And I'll show you on the next slide some figures that show this evolution of the gap. Data come from different sources. This yellow line is JRC estimate. And we can see that from 2001 to 2009, we had just some slight increase from 10 to 15%. That is some historical value. But then with the introduction of binding targets for OEMs, these non-compliance penalties where OEMs needed to pay up to 95 euros per each vehicle, each vehicle sold, and for 1 gram of CO2 in excess, we saw exponential increase. Now it's estimated, the gap, as I said, to be around 40%. This is another graph. Source is ICCT, and it shows distribution of divergence between real-world emissions and type approval emissions. So in 2001, divergence was about 8%, 2011, 24%, and 2015, 40%. And not only that gap increased, but also distribution of gap also increased, and that also show significant individual variability for the gap. On this slide, source is TNO report from 2016, and data come from travel card data from Netherlands. We can see real-world CO2 emissions versus type approval CO2 emissions for different CO2 emitting vehicles from around 90 to 300 grams per kilometer, both for diesel and gasoline. And there is no big difference between diesel and the gasoline. Both showed the same similar divergence. And also we can see that for lower emitting vehicles, lower CO2 emitting vehicles, this gap is mostly positive, while for higher CO2 emitting vehicles, gap can go in both directions, can be also positive and negative, and the distribution is very high. And this is another confirmation that there is really big variability in individual real-world CO2 emissions. And in study that we did in JRC that also confirms previous slides. We had one vehicle that was driven more than 6 months with different drivers, 8 drivers, 218 segments. So it was driven with different driving styles, different weather conditions, tires, with a different number of passengers. And this vehicle has fuel consumption declared 5.5 liters per 100 kilometers, while we got minimum fuel consumption of 4.5, maximum 16.9 per segment. So some average was about 8 liters per 100 kilometers, and that is about 40% higher than declared. Okay, this study is limited just to one vehicle, but just we wanted to see how it compares with all these slides and data that we saw from previous sources. For gap monitoring today, the main sources are self-reporting platforms like Sprint Monitor, Honest John, that can be potentially biased to a certain extent. Then commercial fleet monitoring, or some applications like this mentioned here, green driving tool developed by JRC. Later I'll come back to explain what is this and how you can access this application. So some words, what is the origin of gap? Origin of this difference we can see in test, and we can see in reality. In test, origin we can find in test definition and boundaries. Test in the lab is done, of course, with a fixed temperature, then also with a fixed driving cycle. That is currently NEDC, not very realistic driving cycle, without any auxiliaries, without electrical consumers. Then also test has a lot of flexibilities that one OEM can use to take advantage or not use, like fully charged battery, then using optimized tires for road load determination. Test track conditions can be also during the road load determination optimized using always optimal aerodynamics of the vehicle. While in reality we have higher masses of vehicle, we have more realistic tires, auxiliaries are used, heating, air conditioning. Then also drivers with different driving styles can drive the vehicle. Environment and weather conditions, as we saw, can be very different than what is set in the lab. For example, NEDC test is done at temperature between 20 and 30 degrees Celsius, while we see that average European temperatures and temperatures during winter can be significantly lower. Then also traffic influence results, road conditions, road surface. And what is the current European Commission strategy to reduce this gap and prevent it from growing again? Is new WLTP type approval test that is composed from new driving cycle and a set of new test procedures. Then also European Commission is planning to reduce the gap through market surveillance and in-service conformity testing. This work is in progress. And with robust gap monitoring, this work is also in progress with, for example, onboard measuring of fuel consumption and reporting. Regarding the WLTP, two of the most important goals that we should have in mind to reduce the gap and prevent it from growing again is to keep it alive, to keep alive this WLTP procedure with constant updates, and keep it as representative as possible of average real-world driving, with monitoring, with market surveillance, and in-service conformity. And just now some slides that will explain you how WLTP is different from NEDC and what we can expect with WLTP in terms of CO2 emissions. Development, as you heard this morning from Penny, started in 2009, and the whole development was led by Europe and Japan, with active participation of US, India, and Korea. And China also contributed to some parts of development, and progressive introduction is expected in Europe starting this September 2017 for new types of vehicles. Then next September will be, all vehicles will need to be recertified under WLTP. And all this now starts just for pollutants, while for CO2, still under 2020, NEDC values will be used for monitoring. And for that purpose, JRC developed a correlation tool that maybe some of you heard about, Compass, where WLTP data will be used as input to simulate NEDC CO2 results. And up to 2020, for monitoring of CO2, NEDC values will be still used, and then in 2021, WLTP will be fully implemented for both pollutants and for CO2. Two main improvements is more realistic driving cycle, that is called WLTC, and WLTP that regards to, that is talking about whole test procedure. On this slide, you can see difference in driving cycles. Blue is NEDC, red is WLTC cycle, and WLTC cycle is more dynamic, more energy consuming cycle, represent more real driving conditions. And in terms of a difference in two procedures and their impact on CO2, we can split them in differences that exist between NEDC and WLTP regarding road load determination, lab test, post-processing, and further declared value. With the WLTP, most flexibilities that existed in NEDC are now reduced or eliminated. Also, some errors that have been identified with the NEDC now are corrected. For road load determination, for example, more realistic vehicle mass is used. There is better definitions for the tires, for selection of tires, for tire pressure, for tire tread. Then also calculation of resistance forces is corrected. Inertia of rotating parts is introduced in WLTP, and all that will lead to higher resistance forces that will be later simulated in the lab, and of course will result in higher CO2 emissions. Then also in terms of lab test temperature is now much more strict. It's set to 23 plus minus 3 degrees Celsius. Then driving cycle is more realistic. Gear shift strategy is not more general approach is used that is the same for all vehicles, but each individual vehicle will have its own gear shift strategy driven during the test. Then also preconditioning is changed, vehicle inertia is increased, And in post-processing of results, we can see that now status of battery will be corrected. And also in European level, Europe in its second act is preparing these provisions for correction of speed and distance. So all tests will be corrected to the target speed and the target distance of the cycle, so that flexibility will not be used, hopefully in the future. And then also there is no this margin for declaration of CO2 results that OEM can declare 4% lower CO2 results. And that will be finally approved. So this is now modified. And with the JRC simulation, we see that comparison, what we predict for difference, what will WLTP bring us in terms of CO2 emissions. On this plot, where on y-axis is the ratio, WLTP over NEDC versus type approval NEDC CO2 on average, we expect increase of official type approval values by around 20%. And similar signals we also get from industry, around 20% increase with WLTP for CO2 emissions. And with this, we also expect the gap to be lower. And the effect of WLTP introduction, as you can see on this figure, is expected to be higher for vehicles with lower CO2 emissions than for vehicles with higher CO2 emissions. Now, is WLTP sufficient to take the gap under control? Of course, it is an important step, and important step in addressing this problem. But what will be really in the future, we cannot know now. We need to wait for some years for the testing and for results to see what in reality will happen. And we need a mechanism to monitor the gap, to prevent it from growing again, and to monitor any remaining gap that is left after this WLTP introduction. That can be done through onboard fuel consumption measurement. And as I said, this is work in progress. And also with the market surveillance, we would ensure that production and in-service vehicles are in conformity with vehicles that have been tested. And also we need regular updates of WLTP to maintain alive, and also to cover all future technologies that will come to be more representative of coming hybrid vehicles, automated and connected vehicles. What additional options could be considered in the future to improve reduction in CO2 emissions from the vehicles? We can help upgrade, facilitate the access to fuel consumption information, and that it becomes, of course, it is important information for purchase for consumers now, probably more than pollutant. But we need to improve this even further, and we need to provide online tools and applications that can educate drivers how to drive with the lower CO2 emissions, lower fuel consumption, and promote best practices and information packages to help drivers in choosing their better driving styles. And that brings me back to this green driving tool that I mentioned earlier. This is the tool developed by JRC. And you can find it online on this website, and tell us your experiences. It has been developed using the data from real vehicles, real technologies. and real driving cycles, and also type approval driving cycles. And with this tool, user can choose a route that it will, that route for which it needs information about fuel consumption, and it can choose weather conditions, number of passengers. You can choose, of course, your own vehicle, and you can choose the tires, and then with this information you can see the fuel consumption of your trip, which trip is better for you to choose. So in conclusion, just to repeat again the problem, currently type approval system in Europe that is based on NEDC led to this that I showed, significant gap in real-world driving and type approval CO2 emissions, and that question that led to questioning the whole CO2 legislation for light-duty vehicles. What is currently European Commission doing to reduce this gap and to prevent from growing again is introduction of new, more strict test procedure, WLTP test procedure, and more realistic WLTC driving cycle. Also, it will be addressed through a robust gap monitoring framework and more effective market surveillance and in-service conformity. Thank you for your attention.
Excellent. Thank you very much, Jelica. Are there any questions? Okay, there's one here and a second one over there. Maybe you just start here, microphone's closer.
Hi there, it's Simon Williams here from Marla Powertrain. Thank you for the presentation, it was very interesting. Just got one question on the comment you made about you don't know how big the gap will be, how much you'll close the gap with WLTC to the real world. I'm just wondering what your opinion is, because there's a lot of RDE data now flying around through the third-party testing and manufacturer testing, which is all recording CO2. Surely you can get a bit of a head start on understanding what the gap closing ability is of the WLTC cycle with real-world emissions test data that's available now.
And sorry, what is the question?
Oh, well, have you considered assessing the capability of WLTC to close the gap using RDE data currently available now?
Okay, purpose of RDE was not developed for CO2. First of all, it was developed for other pollutants, and that's why for CO2 we are not sure how representative it is to check the gap. Of course, we always check for our tested vehicles CO2 emissions from the RDE and CO2 emissions from for example, for this vehicle that I showed that we tested for more than 6 months, RDE emissions, of course, you know that you need to validate, you need RDE compliant trips. So with this, you actually don't have whole aspects of real driving covered. In real driving, of course, you can have much more routes covered, so you have a much bigger distribution of fuel consumption. Not only what is now in RDE. So we are considering to use RDE results in the future, but we are not sure that it can fully monitor the gap, because what we see that also for RDE type approval labs are using always the same routes for testing, so not a lot of flexibilities exist.
Okay. Yeah. So yeah, I think I agree that RDE won't be appropriate for fully assessing CO2, but I think just from your analysis at the moment, I think it might be useful, in my opinion, sort of looking at the capability of the changes into WLTC from NEDC and how much the gap could close.
Yes, what we saw probably with RD, we are closing a similar gap with RD compared to NEDC. When we compare WLTP over NEDC, it's similar, 20, maybe up to 25, 30%. What we have from reality can be even higher, so we are trying to find the reasons for this even higher gap that we see.
Okay, thank you.
Thank you.
One here.
Hi, thanks very much. Nick Molden from Emissions Analytics. You said right early on in your presentation that some gap between real world and official is sort of normal or to be expected. Does that actually have to be the case? And actually, I mean, maybe it could be more ambitious, because certainly from our real-world testing in the US, there's on average 0 gap between real-world testing and the EPA 5-cycle fuel economy CO2 numbers. So perhaps we don't have to accept any gap on average at all. Be interested in your thoughts on that.
It is interesting to hear that there is a 0 gap. Because every testing procedure offers some flexibilities. You cannot have a procedure that is very, very strict. For example, you need to have some tolerances in driving style, in a test cycle. So if you are driving within this tolerances, you will have a couple of % of CO2 fluctuation. Then also test temperature needs to have some plus minus degrees Celsius. For each part of the procedure, you have some flexibilities. And if somebody tries to exploit all these flexibilities, you will come up to maybe 5–10%, which maybe we can consider normal.
You're absolutely, at the individual model level, absolutely. What I'm talking is systemically, when you average it across all vehicles across the whole market, whether there has to be systemically an average difference between real world and official.
Yes, about systematic, yes, for this we are not sure it should go only in one, for sure it should not go only in one direction and to be plus 10%. Yes, for that you're right. When I said a certain gap is normal, I didn't mean only plus 10% is normal.
Okay, excellent. Any final questions? Okay, so thank you very much, Jelica.
Thank you also.